Hi guys. So in the last video, we were able to look at Rayleigh's method of solving dimensional analysis problems. We were given a dependent variable and multiple independent variables. We're able to create a single product term, raise it to different exponents, compare with the dimensions of what we're trying to find, and end up with a proportionality expression. So we're able to learn and solve various problems using Rayleigh's method. So what we're going to be doing in this lecture is just conceptually introduce ourselves to the Buckingham Pi method, still of solving dimensional analysis. So it's better and more robust than Rayleigh's method, but we won't be solving any questions in this video. We just want to get ourselves familiar with the necessary concepts we need to understand in order to solve questions when they arise. Okay? So let's get to work. Let's look at where Rayleigh's fails in solving dimensional analysis. So consider a Rayleigh's problem that gives us this as the variable relationship. So let's call this some arbitrary force that we're trying to find, okay? And we know that, okay, by the Rayleigh's problem, we're able to identify our variables, and we can say that the force is a function of, so this is going to be density. Okay, let's call this volume. D is diameter. This is viscosity. Mu is viscosity. G is acceleration due to gravity, and this is surface tension. And let's say this is all equal to some imaginary force F. Okay, this is a hypothetical problem. I don't know of any force that depends on these things, but this is a hypothetical problem. Okay, so let's say we're trying to solve a Rayleigh's problem and we end up with this force expression. Okay, so force is a function of density, volume, diameter, viscosity, gravity, and surface tension. If we were to solve this using Rayleigh's method, we're going to say that F is going to be proportional to rho v d mu g and sigma. Okay, and solving this properly will introduce a constant and raise everything to an exponent, rho to the a, v to the b, d to the c, mu to the d, g to e, and sigma to the f, all equal to force, which will have dimensions mlt to the -2. So the problem becomes very clear very fast. Since we're dealing with, fluid mechanics, we're going to have ideally 3 fundamental dimensions: mass, length, and time. Meaning we're usually expecting about 3 equations thereabouts. But here in this problem, we can see that we're going to have A, B, C, D, E, and F. So that's 6 unknowns. Okay? So we have 6 unknowns and we're expecting to have about 3 equations. So it's not possible. It's impossible to come up with an analytical solution for a problem where you have more unknowns than you have equations to solve the problems. Okay? So in any situation where you have more unknowns than equations, it's going to be very difficult, if not impossible, to come up with an expression or with an analytical solution. So that's where Rayleigh's breaks down. Although it's very good for solving 2 variable, 3 variable, 4 variable problems, when the complexity increases in such a manner and we get up to 5, 6, perhaps 7 independent variables, then Rayleigh is not going to be able to give us an analytical solution. Okay, so that's one of the advantages we have when dealing with Buckingham Pi. So before we get on, we're going to introduce some necessary concepts that will help us understand truly what's going on in Buckingham Pi's method. The first of which is dimensionless quantities. Okay, so what is a dimensionless quantity? A dimensionless quantity is a number with no physical dimensions. Okay, you can't express it as with units of mass, nor length, nor time. Its value does not change regardless of the system of units being used. Okay, so here I have some examples: gain, strain, coefficients of friction. So let's take coefficients of friction, for example. In a regular mechanics course, okay, frictional force is going to be mu r. Okay, so this is the force of friction. So let's just call this friction, and r is the reaction due to the weight of that body. Okay, so let's just draw a diagram. So sort of understand what's going on. We have a body M on a rough surface, okay? So we know that there's going to be a coefficient of friction U, mu, between these two bodies. So what we want to show now is why mu has no physical dimensions. So R is going to be the reaction of the weight on the body, okay? So this is R. Then if the body is going this way, friction will oppose the motion that way. So if we were to make mu the subject of formula, okay? So mu is the force divided by the reaction of the body. But if we were to look at this from a dimension point of view, we know that F is the force of friction. So this is a force. I know that reaction is a force too, since it's in direct opposition to the weight, okay? So at the end of the day, mu is going to have units, Newton and Newton cancel out exactly. So mu is going to be dimensionless. So these and other quantities, other physical quantities can also have no dimension. So let's say take strain, for instance. Okay, so let's say let's call this strain. So strain is extension per unit length. Okay, extension can be measured in meters. So this is extension, and length, this is length. So these are both lengths. So taking this ratio is going to give us a length divided by a length, and this is going to cancel out completely, meaning our strain is going to be dimensionless. Coefficient of friction, strain, and in electric circuits, in amplifier systems, the gain of a system is the output voltage over the input voltage, and we can easily see how this will give rise to voltage divided by a voltage, and at the end of the day, this is dimensionless. So although we're used to properties with dimensions, we have speed, we have acceleration, we have force, and these all have dimensions and units. They are dimensionless quantities that also can be constants. So pi, for example, too, is a dimensionless quantity. Since the formula for the circumference of a circle is pi d, then pi is circumference per diameter, which is a length divided by a length. So pi is dimensionless, 3.14159. Okay, so this doesn't have any units. You can't say pi is 3.159 meters per kilograms or something of the sort. No, it is a number on its own, and it is not attached to any physical dimensions. So dimensionless quantities do not have physical dimensions, and their value doesn't change regardless of the system. So if I have 5 centimeters, for example, if I were to move over to the imperial system and deal with it in inches, it is not going to be the same as 5. But pi in the metric system is going to be pi in the imperial system. Gain in the metric system is going to be the gain in the imperial system, and so on and so forth. So that's what happens when we're dealing with dimensionless quantities. Okay, so now that we've been able to handle dimensionless quantities, we're going to look at the step above that, which are pi terms. The reason it's called Buckingham's Pi method in the first place. Okay, so it's Edgar Buckingham. It's his theory dealing with pi terms. So a pi term is a combination of variables whose dimensions cancel out completely. So every pi term is a dimensionless quantity, but not all dimensionless quantities are pi terms, because you have some dimensionless quantities that are just numbers the way they are, not necessarily a combination of variables. So this table over here is a important constant in ratios, more preferably, not constants in fluid mechanics. Okay, so as we get further, we're going to see each of these fluid mechanics. Okay, so as we get further, we see the derivations and the necessity for each of these come into play, but we're not going to look at them in depth now. All our concern is going to be to create expressions using dimensional analysis. So each of these are ratios of some kind of force or another. Reynolds number, for example, is a ratio of the inertial force on a fluid to the viscous force. Euler's number is a ratio of the pressure force to the inertial force, and so on and so forth. So these are ratios of forces, and because they are ratios of forces, they're going to end up being dimensionless. Okay, so let's quickly show that some of these are dimensionless in the first place. So looking at Reynolds number, you know that Reynolds number is the ratio of the inertial force to the viscous force. So that's rho VL over mu, rho VL over mu. So where is the mass density? So that's going to be mass, okay, mass per length cube times the velocity, length per time, times length, so that's going to be L, times the inverse of dynamic viscosity. So that's m L to the -1, t to the -1, all raised to power -1, okay? So that's m over L cube, length per time, length, and this is going to be length time all over m. So we can easily show that these are going to cancel out, c for t, m for m, and this is going to be dimensionless. So Reynolds number is a dimensionless quantity. Mach number 2, for example, is something you may probably have encountered, and is the ratios of the velocity of a fluid to the velocity of sound in the same fluid. Okay, so when you hear terms like Mach 2, Mach 3, Mach 10, you're simply comparing speeds of a certain quantity with the speed of sound in the same medium. Okay, so we don't even need to do much. Velocity is in meters per second, speed of sound too is in meters per second, so this is going to cancel out completely. So pi terms are combinations of variables whose dimensions cancel out completely. So these are ratios that are constant terms for certain fluids in certain scenarios. But as we come to solve Buckingham's pi method, we're going to create our own pi terms to arrive at solutions for the problems. Okay, so this is Reynolds number, which is rho. Okay, let's take Weber's for example. So Weber's number is going to be rho v squared L over sigma. So that's surface tension. So this means that this is a combination of variables. So we have 4 variables here: density, velocity, length, and surface tension. And if we were to analyze this, we're going to see that this is going to have dimensions that cancel out completely. So for instance, let's say we are dealing with an imaginary question, okay? So let's say f of q. I'm making this up, by the way, rho v sigma and acceleration due to gravity, okay? So let's say this is an imaginary problem we are working with. A pi term for this problem may look something like rho v sigma squared over g, okay? And another one may be f of q g over root sigma. Okay, so just something like this. And when you analyze the dimensions for each of these, the terms are going to cancel out, leaving it dimensionless. So that's what the goal is. You have dimensionless quantities which stand for any quantity that has no dimensions. And within those dimensionless quantities, you have pi terms, which means how can I combine variables to end up with something that has no units? Okay, so that's what's all there is to pi terms. So now we can finally get into defining Buckingham's pi theorem. So if a dimensionally homogeneous phenomenon, okay, so in the introductory lecture, I'll link that at the top. We covered the video after that. Okay, we had a lecture on dimensional homogeneity. So if a dimensionally homogeneous phenomenon, so for sake of rigor, for something to be dimensionally homogeneous means the units of our equation are conserved. Okay, so if f is, let's say, k q b plus root c over d, then the dimensions of f is going to be the same as the dimension of k, and it's going to be the same as the dimension of root c over d, meaning every product term. So this is a product term, this is a product term, and this is a product term. So every product term in our expression is going to have the same dimension. So that's what it means for an expression or a phenomenon to be dimensionally homogeneous, to have the same dimensions. Okay, so if a dimensionally homogeneous phenomenon involves n variables, okay, and these n variables contain m fundamental dimensions, then the variables can be arranged into n minus m dimensionless pi terms. So let's give an example so we can break down what this complex definition looks like. So we're going to create an imaginary scenario, okay? So let's say we have f of q. We know that we're given a term, f of q, and we're told that it depends on density, length, diameter, velocity, and viscosity, okay? So this is hypothetical. F of q depends on density, length, diameter, velocity, and viscosity. So we're going to assume that this is dimensionally, whatever we're going to end up with is dimensionally homogeneous, okay? So it's a function of these 5. And it involves n variables. So how this works is that you're going to have to count every variable involved in this phenomenon, including the dependent variable. So that's going to be 1 f of q, rho, l, d, v, and mu. So that's 1, 2, 3, 4, 5, 6. So we know that n is going to equal 6 for this phenomenon, okay? And these contain m fundamental dimensions. So we know we're dealing with fluid mechanics, and almost always you're going to have 3 fundamental dimensions: mass, length, and time. But to rigorously verify this, you're advised to write out the dimensions for each of the variables and identify that there's no particularly repeating term. So, like so, like so. So if you have something like this, then usually you may end up with 2 fundamental dimensions. If you had just m on one side and this is always repeating as a group, okay? But that won't usually happen in most problems you encounter when solving this. So it's commonplace to see m equals 3 fundamental dimensions. So n is 6, m is 3. Then we're going to have n minus m. So it's going to be 6 minus 3 pi terms equals to 3. So it's 3 pi terms. So that means from our expression here, from our problem setup here, we are going to have a total of three combinations of variables that are going to have no dimensions. So that's the advantage. This is the bedrock on what Buckingham Pi is laid of. You have a certain phenomenon that has certain variables involved that come to create a certain output. You first of all ask yourselves how many variables are here. Ask yourself the number of fundamental dimensions, and you can tell in advance the number of pi groups that you are going to have. So that's the advantage that Buckingham Pi theorem has over Rayleigh's method. Because when doing Rayleigh's method, you're sort of going in blind to your solution. You just make your equation, raise your exponents, and solve them simultaneously. But with Buckingham's Phi, before you even solve anything, you have an idea of how big the solution is going to be beforehand, since you know the number of pi terms you're going to create. So that's one major advantage of Buckingham's Pi. You know in advance the number of pi terms it is going to create. Then the dimensionless pi terms. So this is now going to form the expression that's going to show you the relationship between your dependent quantity and the independent variables. Okay. So let's now look. We've been able to cover dimensionless quantities. We've been able to cover pi terms. We've defined Buckingham Pi's theorem. And now we're going to look at the last important thing before we're capable of solving Buckingham's Pi problems. And that's the concept of repeating variables. In some literature, you may see them being referred to as scaling variables. Okay? So a scaling variable is a variable chosen to be repeated across the other non-scaling variables to create the pi terms. What does this mean? So let's create another hypothetical example. Okay? So f of q is a function of, so let's say it's a function of length, density, viscosity, velocity, let's say area, and surface tension. Okay, so this is an imaginary problem. Our imaginary dependent quantity f of q is a function of length, density, viscosity, velocity, area, and surface tension. So a repeating variable refers to a set of 3 variables that we're going to pick from the total variables we have here that are going to be unique enough to be repeated across the rest. So to understand this, we're going to do a sort of demo walkthrough through what a solution is going to look like. But before we do that, let's now see what each of these repeating variables are. So there are three forms of repeating variables: a geometric, kinematic, and dynamic. What does this mean? If you remember the definition of Buckingham's Pi Theorem, we said we had n total variables. So for this scenario, if you can count, you have f of q. So that's 1, 2, 3, 4, 5, 6, and 7. So here n is equal to 7. So these are the total variables we have. Okay? Then we're going to look at m. So m is going to be 3. So that's fundamental dimensions. Fundamental dimensions. Okay? And remember what we said about Buckingham's pi. If we know m and we know m, we can come up with the number of pi groups we're going to end up with. So n minus m is going to be 4. So these are 4 dimensionless pi groups. Okay? So what does this look like when we're trying to solve a problem? How this works is that we're going to select 3 variables out of this set of total variables for our problem. So that's f of q, l, rho, mu, v, a, and sigma. Okay, we're going to select 3 of these because the total number of scaling variables is going to be 3. So the number of scaling variables is always going to equal the number of fundamental dimensions. So how this works is that you have m, l, and t. So to be able to properly create a pi group, you need a variable from each of these to represent every single fundamental dimension, and you take everyone that is not part and multiply it with the relationship of the other pi groups. So let's walk through what each of them represents so that we can get an understanding of what it means. Okay, so the first pi group, first type of repeating variable, is a geometric quantity. So this is geometric quantities. Okay, geometric. So geometric quantities describe the physical shape or the boundary of your fluid problem. Okay, so some variables you can select as geometric scaling variables are diameter, length, okay, circumference, for example, area, circumference, etc. Okay, so how this works is that you need a geometric variable that will usually have dimensions of only L. So you sort of build up with the dimensions. You start with L for the geometric, and then you need the second type of variable is what we call the kinematic variable. So that's K for kinematic, and this will introduce your time term. Okay, so this now tells you describes the motion of the fluid. So that's fluid motion, about the rate it moves through time. So examples of kinematic scaling variables, here you have velocity, acceleration, and angular speed. Okay, so that's T. And the third type you will encounter would be dynamic variables, which introduce the mass term. So these now describe the mass or the weight of the fluid. So here you may encounter density or dynamic viscosity or surface tension. So viscosity, surface tension. So this is kind of abstract to understand, but when we get to describing the steps involved in solving Buckingham's pi method, and when we get in later lectures to solving problems, you see why this makes sense, why it's absolutely necessary to have each of these classes of the repeating variables. So for a geometric quantity, given this list of variables in our problem, it's an entire selection process of picking one for each of these. So a geometric quantity may be L, length L. Okay. A kinematic quantity to increase our rates, to determine our rates, could be velocity V. And the dynamic to introduce the mass could be rho for density. So there are rules for this, and usually as you solve more problems, you get better at picking and at seeing the norm or the usual variables that fall into these categories. And there are reasons for these too. So there are rules that these guys must obey too. So repeating variables should be dimensionally independent, meaning that you can't have two repeating variables that are dependent on the same dimension. So if one of my repeating variables was L, for length of pipe and D for diameter, so this will have dimensions L, and diameter will also have dimensions L. That is wrong and should not happen. There's no way you should have repeating variables with the same dimensions. Two is that they must contain all fundamental dimensions involved, which is why we said that repeating variables, the number of these are equal to m, which is the number of your fundamental dimensions. Is also why they're grouped into three too: geometric, kinematic, and dynamic. So they themselves must not be able to form a dimensionless group. So let's look at the dimension for length L. So that's going to be L. Dimension for velocity V is going to be length per time. And dimension for m, so that's density rho, is going to be mass per length cube. And if you look at this very closely, since the time quantity appears only once and the mass quantity appears only once, there's no way we can multiply these guys together that will eliminate T for time and L for and M for mass. So it's not possible that these guys, any combination of rho, V, and L, can form a dimensionless group. So that's how we can check it. And lastly, you must exclude the dependent variable. So here our dependent variable was f of q, our imaginary force here. So it is not going to be correct to include f of q as your, let's say, kinematic scaling variable, for instance, since force has dimensions ml t to the negative 2. Okay, your dependent variable should not find itself in the group of scaling variables. So that's what happens when you're understanding and dealing with repeating variables. As we solve problems, definitely we get more used to it. So lastly, let's look at the steps we need to take when solving a Buckingham Pi problem. Okay, the first step is to list the variables. So remember our imaginary example problem. Okay, f of q is a function of rho v a d sigma. Okay, if we were to list the variables, we'll write it out explicitly. F of q, rho v, a d, and sigma. So it also helps, as you list the variables, to write the dimensions of these beside them. Okay, it is very good practice to do this. Okay, surface tension, dimensions for that. Then you count the variables. So that's 1, 2, 3, 4, 5, and 6. So that's going to be n equals 6. Okay, so counting your variables gives you n. Counting your fundamental dimensions gives you m. Then go to determine the number of pi terms. So we know that's going to be n minus m. So we're going to choose our repeating variables. We need one geometric, we need one kinematic, and we need one dynamic if we are working with 3 fundamental dimensions. Okay, then construct each pi term, which means that we'll take our variable. So let's say our repeating variables for this problem are v, a, and d. Okay, it can't work for this, so this is purely theoretical. So how this constructing of pi term works would mean that we'll take a non-scaling variable. So let's say pi 1 is now going to be f of q times the first scaling variable is v, so raise this to a, second is a raised to power b, and lastly is d raised to power c. So this is going to equal m raised to power 0, l raised to power 0, t raised to power 0. And we solve the dimensions of this to arrive at values for a, b, and c that will give us an expression for pi 1. So let's say, for instance, we might end up with pi 1 being, could be f of q v squared over d root a, something like that. And if you perform dimensional analysis on pi 1, you would see that this pi 1 is going to be dimensionless. Every dimension here is going to cancel out. So that's how you construct pi terms. So pi 1 is going to be this. Then pi 2, you're going to take the next non-repeating variable. So that's rho. So you're going to have rho v to the a to the b, d to the c. Okay, and equate this to m to the 0, l to the 0, t to the 0. So these are not going to have the same values. The exponents in for the first pi group are not going to be the same as the exponents in second pi group. You're going to have to solve this one simultaneously on its own. Okay, and then pi 3 for the last non-scaling variable is going to be sigma v to the a to the b, d to the c, and equate this to this as you've done it. So that's how you construct each pi term. So you solve the exponents. So for a, in this example I use a, b, and c. You can use x, y, z. You could use whatever variables you want, as long as you understand that these are the exponents of your repeating variables. Okay, and lastly is that you write your final relationship as the pi term that contains your dependent variable. So the pi term with your dependent variable is going to equal some function of the phi terms of the independent variables and scaling variable. So that's all there is to solving questions with Buckingham Pi theorem. So this is just a purely conceptual approach. We didn't do any numerical calculations here, just to familiarize ourselves with all that happens when we're solving Buckingham's Pi method. Okay, so in the next video we'll get to solving practice problems on this so that we can get familiar with the Buckingham's Pi method, get familiar, more importantly, with choosing scaling variables and handling the exponents. So thanks for watching, and I'll see you in the next video.